Hello everybody, and welcome to this video on logical arguments. So, logical arguments. What is a logical argument? In logic, an argument is a sequence of statements called hypotheses or premises, followed by another statement called the conclusion. So that's what an argument is. Now let's take a look at what a valid argument is. A valid argument has the following property. If all the hypotheses are true, then using the rules of logic, the conclusion must be true based only on the logic of the hypotheses. Here is how I think about valid arguments. So, Mr. Moore is listening to someone making an argument. Here's what goes through my mind when I determine if the conclusion is valid. In other words, it is a valid argument. As the person, I will assume that all the hypotheses are true, whether I agree with them or not. So I assume what you said here is true, I will assume what you said there is true, and so forth. When the person states the conclusion, whether I agree with it or not, whether it is true or not, I look at the hypotheses and see if I can derive, using the rules of logic, that the conclusion has to be true. If I can derive that the conclusion is true based on the hypotheses alone, then it is a valid conclusion, a valid argument. There have been times when I might agree with the person's conclusion, but I do not like the hypotheses that are being used because you cannot come to that conclusion based on the hypotheses. There have also been times when I disagree with the conclusion. In this instance, I either have to accept that I am wrong, or I have to examine the hypotheses to determine if any of them are false. If a person uses a false statement as a hypothesis, then any conclusion, true or false, can be derived. So let's take a look at the truth table for a valid argument. If a valid argument has the following hypotheses labeled H1, H2, H3, and so forth all the way up to Hn, and the conclusion is labeled with a C, then a truth table can be built to determine if the argument is valid by building the truth table for the following statement. So this is going to be a very large if-then statement. So it's going to be if, and then for the if part, we're going to AND together all the hypotheses. So if hypothesis 1 ANDed with hypothesis 2, ANDed with hypothesis 3, and so forth, then my conclusion. So if the above statement is a tautology, in other words, when I build the truth table for this and I get all truths at the very end, then the argument is valid. If the statement above is not a tautology, in other words, there's at least one false, then the argument is not valid. It's invalid. So let's take a look at an argument. So, Mr. Moore is a math professor, or Mr. Moore has perfect vision. Mr. Moore does not have perfect vision, therefore Mr. Moore is a math professor. So for this argument, the hypotheses of this argument are Mr. Moore is a math professor, or Mr. Moore has perfect vision. Also, Mr. Moore does not have perfect vision. So these are my two hypotheses, and the conclusion is Mr. Moore is a math professor. A common way to organize an argument is to stack the hypotheses above the conclusion. So, Mr. Moore is a math professor, or Mr. Moore has perfect vision. Mr. Moore does not have perfect vision, therefore Mr. Moore is a math professor. Now let's convert this argument to symbolic logic. So statement P is Mr. Moore is a math professor. Statement Q is Mr. Moore has perfect vision. So what we have is P or Q, not Q, therefore P, and that three little dot there indicates our conclusion, or the word therefore. So let's build the truth table to determine if the argument is valid or not. So over here we've got our inputs, P's and Q's. We've got to construct P or Q. We're going to have to construct not Q. Those are our two hypotheses. We have to AND together those two hypotheses, and then we have to do if the ANDing of these hypotheses, then my conclusion. So my last column over here is going to be the result of that calculation. So the first thing I've got to do is I've got to do the OR statement with my P column and my Q column. So ORing together columns 1 and 2, true ORed with true is true, true ORed with false is true, false ORed with true is true, and false ORed with false is false. So this is the disjunction, the ORing together of my P column and my Q column. I now have to generate my not Q column. Generating my not Q column, so if I take a true and I negate it, that becomes a false. If I negate a false, that becomes a true. If I negate a true, that becomes a false. If I negate a false, that becomes a true. So this is the truth values for my first hypothesis. This is the truth values for my second hypothesis. I now need to AND those together. So ANDing together those two columns, columns 3 and 4. So true ANDed with false is false. True ANDed with true is true. True ANDed with false is false. False ANDed with true is false. So I've ANDed together all my hypotheses. I now have the if part of my conditional over here. I need the then part on the right side, which is P. So I basically just rewrote my P over here, and now I have to apply my conditional rule. If column 5, then column 6. So let's apply my rule for the conditional. So if I have a false pointing towards a true, that gives me true. If I have a true pointing towards a true, that gives me a true. If I have a false pointing towards a false, that gives me a true. If I have a false pointing towards a false, that gives me a true. So this final column over here, this is all trues, which makes it a tautology. And since this is a tautology, then this is a valid argument. So any argument in this format is going to be a valid argument. Let's go back up to that format. So the format was P or Q, not Q, therefore P. So any argument in this format is going to be a valid argument. All right, let's take a look at an example, another example. I just showed you the example of a valid argument. Now let's look at an argument that is not valid. So here's our argument. If it is raining, then there are clouds in the sky. It is not raining, therefore there are no clouds in the sky. So converting this to symbolic logic, this gives P is the statement it is raining, Q is the statement there are clouds in the sky. So I have if P, then Q, not P, therefore not Q. So let's set up our truth table for this. Oops. Setting up my truth table for this. So here are my input columns, P and Q. I have to do the conditional of P with Q. I have to do not P. And then I have to AND together those two hypotheses. So this is going to be on the left side of my arrow, and then my conclusion, not Q, has to be over here. So I'm going to have to do the arrow statement between this if P then Q and not Q, not P, excuse me, and my not Q column. So let's start building our truth table. So doing the if then statement, my conditional for my P column and my Q column, true pointing towards true is a true, true pointing towards false is false, false pointing towards true is true, and false pointing towards false is true. So this right here is the truth values for if P, then Q. I now need to negate my P column. So negating my P column, so negating a true, that gives me a false, negating a true, that gives me a false, negating a false, that gives me a true, negating a false, that gives me a true. So here's my if-then statement, here's my not P statement. I now need to AND these two columns together. So ANDing together columns 3 and 4. True ANDed with false gives me false. False ANDed with false is false. True ANDed with true is true. True ANDed with true is true. So this column right here is the ANDing together of all the hypotheses. I now need to build the truth values for my conclusion. My conclusion is not Q. So I'm going to have to negate my Q column. Negating my Q column, well, if I negate a true, that gives me a false. If I negate a false, that gives me a true. If I negate a true, that gives me a false. If I negate a false, that gives me a true. So now I've got my ANDing of my hypotheses here, and I've got my conclusion here. I now have to apply my rule for conditional on columns 5 and 6. Alright, so false pointing towards false, it gives me a true. False pointing towards true, that gives me a true. True pointing towards false, that gives me a false. And then true pointing towards true gives me a true. So this final column of calculation, notice I have a false in there. This is not all true. So since this is not all true, it's not a tautology and is therefore not a valid argument. So any argument in this format is not a valid argument. So let's go back up and take a look at that particular format. So any argument in the format if P then Q, not P, therefore not Q, any argument in this format is not valid. And in fact I actually chose this one because this is a common fallacy, logical flaw in their logic that I see when people make arguments. They'll say if P then Q, not P, therefore not Q, and that is not a valid conclusion from those hypotheses. Alright, let's take a look at logical implications. Just as we've seen that there are several rules for equivalence to determine if two statements are equivalent, we also have rules for logical implication. The rules of implication are templates which can be used to create logically valid conclusion from hypotheses. So if you see an argument that has the hypothesis or hypotheses of one of these rules, then the conclusion of our rule is valid. So let's take a look at these rules. So our addition rule of implication. If I have the statement P, then I can conclude that P or Q is a valid conclusion. So an example of this would be, Mr. Moore is a math professor, therefore Mr. Moore is a math professor, or he has perfect vision. That would be a valid argument. The substitution rule, the subtraction rule of implications. So if I have P and Q, then I can conclude that P is a valid conclusion. Modus ponens. If I have the statement if P then Q, and I have the statement P, so if I have these two statements in an argument in the hypotheses, then Q is going to be a valid conclusion. Modus tollens. If I have the statements if P then Q, and the statement not Q, so if these two statements exist in an argument, then the conclusion not P is a valid conclusion. That's modus tollens. Disjunctive syllogism. This is the one that we built the truth table for above. If I have the statement if P, not if P, P or Q, not Q, so if I have these two statements as the hypotheses, then the conclusion P is going to be a valid conclusion. Hypothetical syllogism. So if I have if P then Q, if Q then R, so if these two statements exist in the hypotheses, then the statement if P then R, that is a valid conclusion. Our last rule here is something called constructive dilemmas, and there's two of these. So if I have if P then Q, if R then S, so if these two statements exist in the hypotheses, then a valid conclusion would be this: if P or R, then QRS. Also, if I have if P then Q, if R then S, so if these two statements are in my hypotheses, then a valid conclusion is if P and R, then Q and S. So those are all valid conclusions. Alright, so let's take a look at an example of using these. Alright, so we want to show that the following argument is valid. If P, then Q. P or R, not R, therefore Q. So here's our solution. Within the hypotheses of the argument, we have the following two statements, P or R, and not R. So we've got those two statements in our hypotheses. Using the disjunctive syllogism rule, if we have an or statement and we negate one of those, then that means the other one has to be a valid conclusion. So if I have P or R and I have not R, then a valid conclusion is P. So, for those three hypotheses that we started with, if P then Q, P or R, and not R, a logically valid conclusion to these three statements is these two statements, if P then Q, and P. So now, taking a look at these two statements, from these two statements we can use the rule modus ponens, which says if P then Q, followed by P. So if I have these two statements as hypotheses, then I can conclude that Q is a valid conclusion. And since Q is the conclusion for my argument, then that means that this argument is indeed a valid argument. Thank you for watching this lesson on logical arguments, and I hope to see you next time.